بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so this is the continuation of chapter 3 on statistical learning, and we are now at lecture 2 to present the foundation of predictive modeling in data science. So let me just make a reminder about the previous lectures where we talk about the theoretical foundations of the main statistical theorems that represent the ground for predictive modeling, machine learning, and data science in general. And we have introduced the Bayes theorem, which actually represent how to calculate the conditional probability of an event A given another event B, which is one of the foundational theorems. And we've talked about the law of large numbers, which provide like a confidence when the sample size increases, so the sample mean is going to converge to the population mean. And the third theorem was about what? The central limit theorem, and states what?
States that the average of all average would result to a normal distribution.
Yes. So the average of the sample means, okay, is going to be random, but it will converge to a normal distribution, okay, regardless of the original data distribution. And finally, we concluded by confidence interval, which is a consequence of the central limit theorem. And this means that when we conduct several experiments and we have different type of mean values, so we need to define a confidence interval, okay, of 95%, for example, which is the interval where we have likelihood, okay, of thought that the population mean will be inside that interval, okay, 95%. So we're going to remove the 5% outliers from the right and from the left. And today we're going to apply these concepts, okay, to understand the foundational of predictive models, okay, and this is like an introduction to the concepts of machine learning on how we can make inference or prediction out of the data. Of course, usually people start by doing linear regression, classification, logistic regression, but we are going to learn the science behind all of this. So later on, if we apply to any other model, we're going to apply the same theory that we are going to discover in this lecture. Does this make sense? Okay, so the lecture will be a little bit theoretical, but I complement the theory with examples and also with Python coding to illustrate this concept as we have been doing in the previous lectures. So again, just some general definitions about statistical learning and machine learning as we discussed several times. So statistical learning, this represents the foundation of machine learning, and it basically deals with model interpretations and quantifying uncertainty. Okay, and machine learning, it's basically deals with large-scale predictions, okay, learning from the data to make prediction or to make inference about that data. And the main issue in data science is to optimize a function. It's basically all data science or machine learning problems is basically a function optimization. So what does it mean, a function optimization? Usually when you have a function, you want to optimize, for example, you want to find the minimum value or the maximum value. Okay? So this is basically the optimization that we talk about, yes. It's usually we use derivative. For example, imagine that you want to find the maximum or the minimum value of a function. And this usually corresponds, for example, if I want to find this minimum, this corresponds to what? A derivative equal to 0. Okay? So it will be flat. Okay, flat derivative. Okay, so this is on one-dimensional. We usually calculate the derivative to optimize the function to find the minimum value. Imagine that you have a function that represents the error. So what you would like to do with the error? You want to minimize the error.
Yes.
So you want the error to be almost 0. So imagine that this error will be kind of complex function, and you want to find the lowest point into that function. Now, this is in two-dimensional, everybody understand, but usually when you do machine learning, we will have multi-dimensional. This is three-dimensional only, but it can be dimension of thousands. Okay, it's something that we cannot imagine because we can only print in 3D. And the objective is the same. You know, when you do derivative in two-dimensional space, we call it gradient in multi-dimensional space. Okay, and this is why we call it gradient descent. It's basically you want to calculate the gradient that will descend over a certain slope, like this. And this is just a generalization of this two-dimensional curve. Okay, but usually, and what we are going to represent as a function is basically a loss, or what we call, in more general terms, the objective function. It can be a loss, it can be a reward, okay? And it should be minimized so that we can have a best fit, okay, of the model with respect to the data that we would like to predict. When we reduce the error, it means that your function is able to convert the input features into a correct output. This is what we do. This is prediction. Okay, you have an input feature. For example, you want to classify an email whether it is a spam or not a spam. We're going to create a function, J for example. You provide an email, it gives you an output, okay, spam or not spam. And you want to minimize a certain loss function. Of course, the design of the loss function or the error function is very important because you're going to apply gradient, okay, in many iterations so that you will reduce the error on the data that you will be using it for to build your model. Okay, so the objective, as already mentioned, is to identify the optimal model, and the optimal model is the one that minimizes the error between the predicted values and the actual values. And this is what we do in supervised learning. In supervised learning, we have input known, the real output is known, and you want to make a mapping between these two through a function so that the function will produce something very similar to the actual output that minimize the error between both. And the technique used, as already mentioned, is the derivative, which we call gradient, so we call that a gradient descent, and it has a lot of applications like maximizing the recommendation system effectiveness, okay, and enhancing the weather forecast. I want to make, for example, what will be the weather after a couple of days with minimum error, or detecting whether an email is spam or not spam, and so on. These are typical examples of machine learning models. And of course, we need to go through the math foundation, how to represent this problem mathematically, because an optimization problem is basically a math problem. It's a function. We need to make a model of that function. Okay, so let's start from this picture. Usually now, when you develop a code, traditional programming, what you will do? You have a data, and you will develop a program. So yourself, you're going to develop a program that will calculate the average, or you'll develop a program that will, I don't know, transform the data to another shape, or whatever things you've been doing. Okay, and it will provide the output. So you have the data, you develop a program. Okay, for example, I can give a list of prices, and I want to calculate the total, or a list of grade, and I want to calculate the average, or any kind of program. This is what we do. We have the data. We will develop the algorithm, okay, which is by a program in Python, in C, in Java. It will provide us the output. Because the program, the transformation between the output and the input is known by some models. There is a known model that can make this transformation. I know it. Okay, it's a function. If I want to calculate the average, okay, how can I calculate the average? I will make the sum divided by n, and I will find the average. So the equation or the model is known in advance. So I can program that model. But now, in machine learning, it's different. I have the data, and I have the output, but I don't have how to transform that data into an output. So the paradigm in machine learning is different. It's not the same as the traditional programming. I can provide you, for example, like we did in the major exam data, and I say, okay, make me a prediction what would be the final grade based on the major exam. Do you have any algorithm that can do that?
No.
Usually no. Okay, it's difficult. Or for example, I can give you some weather conditions in the past, and I tell you what could be, for example, the temperature after 2 days. Okay, or people now use this in the stock market for financial transactions. Okay, and there are so many applications. Okay, so, and this is why now, how we do, this is the typical way on how we develop a machine learning model. So we're going to have this data, and this is the simplest way, the supervised learning. I have the data from one side, the output from the other side, and I will train an unknown function. It's unknown. And the role of training is to minimize an error between the predicted output and the real output that already have in the beginning. Okay? So the objective is to find a function j that will convert the input feature vector, so this is a feature vector, okay, into an output y hat. This is the estimated or the predicted output. So this predicted output, in the ideal case, it must be equal to the real output. But in general, it's not going to be equal. I don't have the transformation in the beginning. So there is an error. And the objective of the training is to keep minimizing the error by applying the gradient descent, which is just doing the derivative equal to 0 and try to optimize with all the data that we have. Okay, so let's see a few examples. For example, if you have an email spam detection, a function j that we don't know should convert an email or an email feature into either 1 or 0. This is what we call classification. I'm going to classify emails into spam or not spam. So j is an unknown function that I need to find that will be able to make a correct classification. Of course, there is no 100%, but if I can reach something around 99%, 90%, okay, sometimes 80% would be fine, depending on the scope of the work, that would be fine, okay? And weather forecasting, imagine that you have temperature and humidity as input, and you would like to make a prediction what would be the weather in the future, for example. And these are examples of mathematical formulation, okay? We can have gx, for example, as a linear combination of the feature vector. Imagine that you have a feature vector x, it contains x1, x2, x3, these are the features. And you remember, we talked about the feature. What are the features? It's the most important data in the data set, because not all the data can contribute to finding the output. And then there are unknown parameters. Look, beta 0, beta 1, beta 2, beta n, they are completely unknown. Okay, and I need to find the best combination of these values that will minimize this linear regression model. And it can be the simplest. If I have only one feature, it will be the equation ax plus b. So I need to find two parameters, a and b. Okay, and of course we work on multi-dimensional space, so basically it will be matrices and vectors. Yeah, and in binary classification, so usually we have what we call logistic regression. So when we say logistic regression, it means the output is either 0 or 1. Always have in mind, logistic, it means, okay, it's usually the log, which can be 0 and 1. Okay, and this is the equation of the logistic regression. The probability of y equal to 1 given x is equal to this equation, 1 divided by 1 plus exponential of the sum of the features, the weighted sum of the features. So when we talk about learning, so these parameters are learnable parameters. What does it mean, learnable? We're going to define their exact values from the data. And I will show you some examples later on. Okay, so imagine that you have a data set of houses and you have the feature that is the number of room, and you have the corresponding price of the house. For example, I have this house, it has one room, and it's almost 150. And this is another house, another house, another house, another house. And you see now, I want to make a model that, okay, if I have 4 rooms, what will be the value? Should I consider here, here, or here? Okay, there is no model that can tell me what will be, for example, the price or the estimated price or the best guess of the price for a number of rooms. And for that, we're going to take this data set, we're going to train a model that will minimize the error of any other number of rooms. So in these particular cases, usually, we're going to have a linear regression. And in our case, we have only one feature. What is the feature that we have here? Number of rooms. Okay, so we will have just an equation, beta 0 plus beta 1 x, or beta 1 number of rooms. And finally, if I go further, if I make my optimization, I will find a line. This is why we call it regression. Okay, it's this is the regression line. It will, and this regression line is the closest possible to all the different houses points. Okay, so what does it mean the closest to the house? يعني it will minimize the distance between any point and the line. يعني ممكن تكون عندي line هكذا أو another line, for example, just a little bit skewed like this or like this. So I want to find the best model that will minimize the error, okay, the error to the point. If I have this model now, because now I have the input feature that is the number of rooms, and I also have the price. And from that, I'm able to make the best guess of a model, which is just a linear regression model. And this will allow me to identify with high precision. That could be not the real value, but this is the closest value to the reality based on the information that I have. Of course, if you add additional points, that would change your parameters A and B, or beta 0 and beta 1. You understand the concept?
Yes.
Okay. So all the deal in machine learning and in data science when we have data to train is to train these models, okay, such that we reduce the error between the points and the model. Now this is a simple model. We can have a logarithmic regression model, an exponential regression model. And the most important thing in any case, whatever the complexity of the model is just to reduce the distance between the points and the model. واضحة النقطة ولا لا؟ Reduce the distance between the points. This is a point. I want to reduce the distance between the point and this model. So this is the optimization, and you will have complete lecture about linear regression, how we can optimize to find the best guess of these parameters, these learnable parameters. Okay, now this shows a little bit better the gap. So imagine that you have these different points and you want to find the best guess. So what you will do, you will try different lines. You will start from a completely random line, A random and B random. Of course, it's going to give you high loss. And in every iteration, you take a couple of points, you calculate the error, and you say, okay, let me make the derivative to find the minimum. And this derivative is going to give you a better version. And you keep doing that multiple times, yes.
So when you calculate the error, you calculate the distance between each point and the line.
Yes, now look, the error among all the points, now I have a distance here, I have a distance here, I have a distance here, so I will try to take the average of all the, okay, it's not really the average, it's the least square error, but kind of a loss function that will model this error.
But how do you get the derivative? If it's a value?
No, the derivative will be on a function. The function here, it's ax plus b. Here, in this particular model, we have a linear function. That's the simplest. So the derivative of ax and b, the derivative with respect to a, and the derivative with respect to b. Okay? We will see this in detail. Now, I want you to understand the concept of loss and error. That's the objective of today, is to understand this concept. And later on, we will see what are the strategies to teach a model the correct parameters. Okay? How the model can learn the correct parameters. Okay. And now we talk about the loss function. It's important. لأنه everything I'm saying right now, it's applied to the most complex deep learning algorithms. Everything is based on these foundational, okay, concepts. So look at the loss function now. We need to define a loss function that will capture the difference or the discrepancy between the predicted value and the true value. I think the concept is clear. Okay, and this is essential to train because this loss function this is the reference that we are going to use to optimize. The optimization is not going to be random. You make the derivative of what? Of a function. What is this function? The function that models the error. What's the error? It's the difference between the predicted and the true. We're not going to make like the base difference, x minus y. There are sophisticated methods that will optimize. And of course, the loss function for the same problem, you can have different loss functions that apply to the same problem. And in this case, you can try different combinations to see which one would work better. I can make, for example, in this particular case, I can make try to minimize the sum or the difference of the average difference between these functions. The absolute, of course, the absolute value of the difference. It's not going to be negative and so on. Or there are different ways on how to do that. Okay, so the loss function in prediction models will depend on whether it is a regression or a classification. And to talk about regression and classification, so regression basically when the output is a real value. For example, in case of estimating the price of a house, we will have a real value, continuous. So here we talk about regression. And when we classify, for example, here I would like to classify whether it is cold or hot. In this case, we talk about classification and why we'll have a finite set, discrete, okay, representation. Okay, and this is what we call categories usually. And for example, for regression, especially for real regression, we use what we call the squared error loss. You can use the absolute value between y and y hat. Y hat is the predicted. Like in a better squared model, I mean better, it's with experiments that people say this works pretty much well. Okay, it's y minus y hat square. Of course, in any case, it will return a positive value. Okay, and this will be only on one point. So we take one predicted value, one real value, we make the difference. And usually we're going to estimate over several points. So we will make the sum. And in classification, 0-1 loss classification, or we call it also binary classification. Binary, it means the output will be 0 and 1. For example, for spam detection. For spam detection, you have an output either 0 or 1. So in this case, sorry, in this case, the loss will be equal to this formula. What is this formula? What does it mean?
Loss is equal to
1, if y is different from y hat, if the predicted value is different, for example, you have spam and not spam. Your prediction model gave you not spam and it is spam. So the loss will be 1. It's high. And if your predicted model give you spam and it is actually a spam, so I'll make the error is 0 because it makes a correct classification. Okay, so this is very simple. It's either 1 or 0. But we're not going to, okay, these are some other possible loss values. For example, instead of squared error loss, I can use the absolute error, which could be y minus y hat. And it's positive. Because if I'm going to do that over multiple points in the data set, it will be a sum. And if the sum has positive and negative, it's going to cancel itself, whether still there is an error. So I'm going to accumulate the errors, whether they are positive or negative. The squared error or the vector norms also. Okay, we calculate the norm of the vector, which is the scalar product between the two vectors. Huh?
You subtract the negative vectors?
Yeah, the norm. You calculate. So you don't subtract. It will result to a positive value, the norm. Okay, it's the dot product between two vectors. Okay, so the vector norm, and it can be squared or normal. All these are possible loss values for a regression model. And for classification, you can use cross entropy for probabilistic classification or hinge loss used for SVM. So we will see this in future lectures. Okay, let's take one example. For the regression, the squared error loss. So, so this value, the value of the loss, this is what we calculate over one point. You see now we have a distance here and a distance here. Here, it's y. This is the real y. This is the real y, and this is the predicted y. So the difference is negative here, but I'm going to make square, and here it's positive. I'm going to make square to have always a positive value. But if I have several points, so I need to calculate the loss for all the points, not on only one. So I will make the sum. It's a cumulative, okay? And I will divide by n to have the average. Okay, so I will just accumulate all the errors, divide by n, I will have the average error. And this is why we call it the mean square error. Mean, it's average, and square error, it's because we do y minus y hat square. And this is the equation, pretty much simple. So I'm going to take point by point, calculate the square difference, sum everything, calculate the average. And this will be, in the ideal case, the value should be equal to 0. But if I start randomly, it will never be 0. So I will try to push it towards 0 as much as possible. Okay? It's very difficult to reach 0, but if you have 0.01, or you can make a condition when you want to stop training more your data. Okay? And so this is what we want to minimize, the sum of the squared root. This is what we call the square error loss. And we aim to find the model parameters that will minimize that value using derivative. Okay, now the model is very simple. At least I know how many parameters I have. How many parameters I have in this model? 2. The slope, A, and the bias, which is this offset. This is what we call the bias. And this is, we call it, okay, the slope, but in machine learning we call it the weight and bias. And basically any machine learning model, it's a collection of weight and biases. There is just a startup in the US, it's called Weight and Biases. They work on deep learning, okay? And now we have weight, that is the slope, okay, coefficient, and we have the bias, which is the offset here, yes.
Doctor, do we always represent this equation on linear regression, or it depends on the graph, or it depends on the way the data is given, or how the data is...
Yeah, this linear regression, because you have one input feature and one output. But if you look at machine learning model, it's basically a multi-dimensional, it's regression or multi-dimensional classification, because the regression is not always linear.
Yes.
It can be exponential. It can be logarithmic. It can be something completely unknown. And this is most of the cases what we'll do. Okay, so we're going to have, like, imagine like ChatGPT has 175 billion parameters, and they need all to be tuned to converge. So the scale is huge. And now we talk about trillion parameters models, the next large language model generations. And this is why to tune these parameters, imagine that, everything we do in small scale, it applies to larger scale. The only difference is to have the computing capabilities. And of course, there are many optimization in terms of how to train the model from parallel computing perspective. But let's focus on the concept. Imagine that you have only 2 points. And this is now, it's related to the law of large numbers and also to the law of central limit theorems. Imagine you have only 2 points. We will be able to derive a model, but will this model be accurate? It's difficult. Imagine you have only 1 point. If you have only 1 point, you can draw any line going through that point. So it doesn't make any sense. 2 points, you can have one line between the 2 points, okay, but you not necessarily have other points close. So as you increase the number of points, as you will be able to calculate more errors, and the average error is going to converge to a normal distribution, and then we can have some kind of confidence if we do that over multiple samples. And this is why we train over different samples to see what will be the average loss here, the average loss here, and the average loss here. If they are close together, I can have a confidence. If they are not close, okay? Yeah, this is why we make the whole introduction about the things, okay? To have a clear understanding about the convergence of these models. Okay, so basically we're going to look at the mean model over a certain sample, okay, and we can, the best practices is that I train on different samples and then compare all the different means of the loss, saying if they have a confidence interval that is small enough to say I have certain confidence of that model. And so the scale of data will play a very important role, a very important role. Okay, so basically we're going just to do the difference between observed values and predicted values on that regression line. That's a simple code. It shows the square error loss in data science. So here I've taken the data set of temperature. I calculate, so now I have a row of temperature, okay? I will make a bad model. What is a bad model here? I will consider all prediction will be just the mean. It's a prediction. If I take all my values and just make the mean, and I will say this is a prediction. Of course, calculating a mean on one sample is not going to be accurate, but okay, let's assume. So if I assume that I have a mean as a prediction, and I would like to calculate the mean square error, which is basically here we apply the formula. Okay, it's the sum of all errors. These are the predicted differences, predicted temperatures. Okay, so this is the mean in all the rows. And then I will make the difference between actual temperatures, the predicted temperature is just the mean, multiplied by the square root in all the range, and divide by all temperature values. So this is going to give me a mean square error of 20. Okay, it means in average, if I divide this, okay, if I make the square root of 20, 6 degrees, okay, or 4, 5, yeah, it's between 4 something, yes. So I will have 4 degrees difference in average, plus minus, okay. So that's an estimator. That's a possible estimator of predicted model, and it gives, but usually we need to reduce this to be closer, as close to 0, yes. I cannot say a variation of 4 temperatures is a good estimator. It's big, okay, somehow big. Okay, so that was an example on regression, and this is the second example on classification. The 0-1 loss, or also we call it the binary loss, which lead to a value of 0 and 1. And basically, as already introduced, it will lead to a loss between y and y hat equal to 1 if the outcome is different. And it's used in different applications, in classification tasks, as already mentioned, spam or not spam, or different usages. And okay, and we have also the cross entropy, which is a little bit, it's also used for classification. Instead of making 1, we're going to check to measure the distance or the difference between the true and the predicted distribution, not values. So this is why we call it entropy, because the distribution basically tells us information about how the data is distributed, and this is what we refer to the entropy. Cross entropy, because we are going to compare the entropy of the true value and the entropy of the predicted value. So look, for the same classification problem, I can use a binary classification. It can lead to a model, and I can say, okay, let me use a cross entropy classification, which will try to minimize the probabilities, okay, the discrepancy between the probabilities of predicted probabilities and the true probabilities. And here we use the log for the predicted probability distribution. And this is the equation. It is the sum, okay, so of yi log y hat I. So this is the actual, this is the predicted. Okay, plus, and this is for the true case, and this is for the other case. And we use the log here because the log is going to make, when you have small errors, they will turn into big. Okay, for example, the log of 0 is going to give you very negative values. So it will affect on the error. Okay, log of 0, when when this value, the probability of predicted distribution is very low, so it's going to penalize the difference with respect to the correct value. And also it keeps the number manageable as compared to the real values. Okay, and here, and also it has the ability to measure the surprise. The more unexpected a prediction is, the higher the log value will be. So this is a way to penalize the errors more and more. Okay, we can add additional functions, like sometimes exponential or logarithmic, to penalize the error in the loss function, because we want to push the error to be the smallest possible, so the model is the closest to the prediction. Okay. So the loss function that we calculate upon a data or a data set is based on just that data on that sample. It doesn't give, if I change my data, I'm going to have probably a different loss. So the objective is not only to calculate the loss, but to have a good estimate on all possible losses across different samples. اللي هو في الأخير the average of these losses. And this is what we call the risk. So the risk, predictive modeling risk. So the risk is basically like we seen in central limit theorem. We calculate several averages, and it's going to be a certain normal distribution. And the risk is just the expected loss among multiple samples. واضح ولا؟ So if I try to run the loss function on a large number of samples, using the law of large numbers, is going to converge. So the loss is going to converge to the population loss, which we call the risk. Okay? Usually, this is not feasible in practice. I cannot have the exact value because I don't have these distributions. So I'm going to use my data to try to estimate the risk by running the models or the training on different samples. Every sample is going to give me a loss, making the average of all these losses. This is what is going to define the risk level, of the predicted model. So the risk quantifies the expected loss. Expected يعني الافرج، متوسط اللوسز الموجودين، متوسط. Across a data spectrum or across multiple samples. And RG represents the risk associated with the prediction J. So I have a function that converts, for example, number of rooms to prices. And this will be the risk. The E denotes the expected over joint probability between X and Y. L is the loss over a sample. And S is the true value. Y is the true prediction. And GX is the predicted value. As already mentioned, in general, we are going to estimate the true risk by calculating the empirical risk. الامبيريكال دائما مبني على بيانات. So basically we're going to run the empirical risk. It's basically the same formula, but this is going to be over, look now, here it's the expected. Expected, it means the average over the infinity. But usually we don't have an infinity of samples. But I can have, if I have a huge number of samples. So this is the loss in every sample. And this is why when we train in machine learning, we train in batches. ايش نعمل الآن؟ عندي training data set. I will take a batch. هذا مثلا this is a sample. مثلا batch فيه 16 features. مثلا عندي 1000 feature. I will divide them into 16, 16, 16. So I will calculate the loss over the first 16 values, the second 16 values, the third 16 values, and then I will average over all the loss, and this will be the loss of one training pass. Because the training pass is going to go over the data set sample. Yeah.
This Dr. Epoch?
Yeah, and we train multiple epochs to train, to extend the convergence, over the data. Yeah, we go through multiple iterations. And you see, it's nice how things are related with each other. Later on, when you'll go through neural network and machine learning, you'll have everything clear in your mind. Because everything is related to this theory. This theory is very important. Yes?
So in practice, we use the empirical risk.
In practice, there is mostly the empirical risk, but we try to converge to the optimal risk. This is why we try to train, we train for 500,000 epochs, and we try to increase the batch size. And there is a balance between when you increase too much, when you decrease too much. So there is always a balance, but we try to optimize, we try to converge to the true risk values by calculating over multiple iterations, the different losses, averaging around them, and go over another epoch to train more and more. And of course, now when we calculate the risk, the objective is to minimize the risk. Now, we talked about minimizing the loss through the gradient, but also I need to find what is the risk minimization. I need to find the minimum value of the risk. Okay, I need to find the model G star or the model G that will minimize the risk across all the values, all the samples. So it's another optimization. You optimize on the sample and then you try to optimize over multiple samples to be closer to the population mean of the risk. And imagine now you have multiple losses and you want to calculate, okay, this average loss could represent a best fit, okay, or a best estimate for this optimal loss. Okay, I want to have the minimum loss, okay, or the optimal loss possible. And for this, I need to find G star. And what is G star? It's basically the last model that you will find. The predicted line, for example, in the case of linear regression. This is the best estimate of G star. It could be probably not the best estimate. If you add more data, it's going to change. Okay, so increase the data, if you do your training very well, is going to converge somehow, with some confidence, to the best to the best model. Okay, so the risk minimization, try to identify and fine tune a prediction function J that minimizes the expected loss, the risk. So you expect one loss, the loss it will be minimized several times, average it across all data points in the distribution Y, X, and Y. Okay, so if we don't have the whole population, we're going to use different type of samples and averaging among all of them. This is also what we call cross-validation. We'll see this when we talk about machine learning. Okay, and RG is defined as the expected loss between Y and G. Yeah, so GX is a model that we learn from a data sample, GX. G star is the best model ever that we can learn from the data. That's the difference you should have in mind. So in any case, when you develop, you're going to develop a model, but you aim that this model, try to converge to the best model. You can never say I have the best model. The best model will give you always 100% the correct answer. That's almost impossible. Okay? Even if it is 99%, it can fail. But we try to minimize the failure, especially when your model is very, very complex. Because in general, in linear regression, it's very difficult that you have a pure linear model. In this case, you don't need prediction. Okay, you have always a variation, but we try to minimize the variation. We can always live with uncertainty, but when this uncertainty is bounded. See what I mean? Okay. Yeah, so every model, it's a model that you learn from a data sample or multiple data samples, and we aim at making this the best model possible, okay? When you have the real distribution of data, in this case, we can build the optimal model. But if you don't have the real distribution of data, it's an empirical distribution.
So it all depends on the data.
Yeah, because it's the data that is going to build, And this is why we usually work on empirical risk minimization, which is going to be the argmin. Now, this is the notation. It's argmin. Okay? It means we are minimizing the empirical risk, okay, over all possible models, J, and this is what will represent the best guess. Okay, this is what we will actually find, and we will try that this one try to be as close as the J star. So this is an empirical model that we learn from the data sample. Okay, I'm going to stop here.